Hey guys, we're going to tackle a real big bear today, and we're going to talk about introducing ourselves to these imaginary numbers. And we're going to invest quite a bit of effort in just trying to set up the little background on why we even need imaginary numbers and how they're even useful as we get into higher levels of math. But first and foremost, by the end of this video, these are some of the problems that we hope we can solve. We're hoping that we can solve, and simplify some expressions like I to the 23rd or I to the 23rd times I to the 54th. And this crazy looking letter I that you're seeing is what we call the imaginary unit. So we're going to define that shortly as we get going. And you're going to be able to add and multiply and do all sorts of fun things with these imaginary numbers before this video is over. So as far as number systems go, and I bet you were probably really good at identifying these number systems, maybe, in eighth grade or such, but we've gotten away from them. So I want to do a quick review. And we're just kind of walking our way through the history of math. And at the beginning of math, way back in early civilization, we started off with what's called natural numbers. And that's 1, 2, 3, 4, all the way to infinity. Then at some point they decided, well, we really need the number 0 to represent nothing. Like we have killed 0 deer today to eat. And so when you combine the natural numbers with the 0, we created a new number system called whole numbers. And those whole numbers worked really good for a while. And all of a sudden, they decided they needed negative numbers. So when you combine the whole numbers with the negative numbers, you get a new number set called integers. So integer starts at negative infinity, and it counts all the way to positive infinity and hitting every integer along the way. Well, integers worked good for a lot of things, but then, what if you needed a half or, 2/3 or some type of fraction? So when you combine the integers with the fractions, we created a brand new number system called rational numbers. And there's a lot of goofy jargon here, but maybe this is the simplest. Any number that can be expressed in the form of a fraction, such as p divided by q, is a rational number. And again, those worked great for a very, very long time until the equations got difficult enough where we needed to incorporate what was called irrational numbers, like radical 2 or maybe a pi. So the combination of rational numbers with irrational numbers make up our real number system called real numbers. And then all of a sudden, that's kind of where we're sitting at this current day. We've covered everything within real numbers, but we're going to run into some equations that are so complex that there is no solution within the set of real numbers. And so we created a need for imaginary numbers. And I'm going to actually backtrack just a hair. Here's a really nice graphical organizer that's kind of just organized, upside down compared to the last one, where we started with those natural numbers are at the bottom down here, and then we worked our way going up. So you'll see at the top, we're sitting here with real numbers. And if you combine the real numbers with the imaginary numbers that we're going to introduce you to today, you get a brand new number system called complex numbers. And I'm going to add the word complex up there at the top. So it's just kind of a nice graphical organizer to give you a visual of how all these systems, interact with one another. So I want to establish a need for imaginary numbers. And as we work our way up there, we're thinking, as the complexity of our equations grows and evolves, the need for a more diverse number system grows as well. So for instance, let's go back to our really early civilization days. If we were only working within the set of natural numbers, we wouldn't be able to solve the equation x plus 5 equals 2, because we know that if we subtract a 5, we're going to get x equals -3. And -3 is not a member of the natural numbers. And that's what kind of spurred on this need for the integer number system. However, if we were only working within the integers, although they worked great for the last equation, they wouldn't work good for this equation right here, because after you add the 5 and divide by 2, you get ourselves a fraction or a decimal. So we needed to create this rational number system. And although the rational numbers worked good for that one, when we get to this next equation, x squared equals 5, the rational numbers couldn't solve this. Because when you take the square root of both sides, you're getting x equals plus or minus radical 5. And again, that created this sense of urgency to create the irrational number system, which combined with the rational numbers made the real number system. So not to get too confusing, but we're building up to this ultimate point here today. And you can picture the drum roll in the background. If we're only working within the real number system, which is what we've been working with up to this point in our career, we can't solve this equation right here, x squared equals -4, because there's not a real number that you can square and get -4 as the answer. So we had to create the imaginary numbers in the complex number system, and that's what we're hopefully going to be able to do by the end of this video. Okay, so our first major definition. The letter I, which we call the imaginary unit, okay, let's clarify that. The imaginary unit is a big fancy term for the letter I that we're going to see from now on. It is defined as the number whose square is equal to -1. So I squared equals -1. That's worth highlighting in a big way in our notebook. Now, there's a lot that we could take and run with there. In fact, what if I just said, you know what? If I know I squared equals -1, what if I took the square root of both sides? That would simplify to I equaling radical -1. That's also worth boxing in, perhaps. And that'll actually come into more play in our next video when we're simplifying radicals that have negative numbers underneath them. But the main point today is we're going to take, let's see if we can switch up. We're going to take advantage of the fact that I squared equals -1 by definition, and we're going to really dive into the powers of I. Okay, so here's a chart that we want to try to fill in together. And what we're going to do is we're going to look at the powers 0 through 3. So we're going to do I to the 0, I to the first, I to the second, and we're going to do I to the third power. Okay, so for some of these, we won't have to use the rewrite column or the substitute column. That's more for the later rounds. But what we know throughout all of mathematics, anything raised to the 0 power is always going to equal 1. Okay, anything raised to the first power is simply itself. And then by definition, we said that I squared is equal to -1. So the first one that I'm going to rewrite is I cubed, and we could decompose that into I squared times I. And we know that I squared is -1. And if we multiply those two together, we'll get -I. So look at the pattern we have here and kind of keep this in the back of your memory bank. We went from a 1 to an I to a -1 to a -I. All right. Watch that same pattern reemerge here as we get a little more complex. So we're going to do powers 4 through 7. So we've got I to the 4th, I to the 5th, I to the 6th, and I to the 7th. I to the 4th could be decomposed into I squared times I squared. Of course, you may be sitting there thinking, well, could I do I cubed times I? And you absolutely could. I think that one's just a little bit more complex, and I went with what I thought was the easier one, because each of these I squareds is equal to a -1. And the product of those two is +1. I to the 5th is going to be, you could decompose that into I cubed times I squared. The I cubed is -I, as seen earlier, and I squared is -1, and the product makes +I. Now, how about this one? When you see I to the 6th, I was thinking, let's do I to the 4th times I squared. And again, there's a lot of other combinations you could break that. Some people decompose that into I to the 5th times I, or maybe I cubed times I cubed. You could do all of those. But for me, I to the 4th is 1, and I squared is -1, and the product is -1. I to the 7th could be decomposed into I to the 4th and maybe I cubed. I to the 4th is 1, and I cubed is -I, so the product is -I. And I think you're seeing the exact same pattern that we saw earlier, right? It went 1 to I to -1 to -I. Let's do one more table, and just to confirm that the same pattern does emerge, and we'll continue to kind of build our confidence as we try to decompose these rascals and get a hang for this. I to the 8th, we're going to try to do I to the 9th, and I to the 10th, and I to the 11th. I to the 8th can be decomposed into, we'll say, I to the 4th times I to the 4th. And we saw in the last table, that's just 1 times 1, which makes 1. I to the 9th could be, I'm going to go crazy here. Let's do I to the 8th times I, right? Basically, if you're scratching your head on how I'm rewriting these and so-called decomposing them, all we're doing is we're making sure that this exponent and this exponent add up to the original. As long as that's true, you could do 7 and 2, 6 and 3, 5 and 4, any pair of numbers that add up to 9, of course. And I to the 8th is 1, I to the 1st is I, and the product is I. I to the 10th could be, let's see, what could we do with I to the 10th? What if we did I to the 9th times I? I to the ninth is I, and I is I, and the product is I squared. But don't write I squared down. Ask yourself, what is I squared? If that's equal to I squared, that's just -1. So maybe the one thing you take away from this video, if all else fails, you're going to say to yourself, every time I see I squared, replace it with a -1. If that's the only thing you remember, you're going to be in pretty good shape. All right, last but not least, I to the 11th could just be decomposed into I to the 10th times I. I to the 10th is -1, and the product makes -I. And again, we're seeing the exact same pattern. We're going from a 1 to an I to a -1 to a -I. So let's see if we could summarize this with the idea that it's just going to continue to perpetuate itself over and over again. For me, this is how I like to summarize it. I use this wheel. In this wheel, I do I to the 0 is equal to 1. I to the first is I to the second is -1. And I cubed is -I. And then the cycle just keeps going around and around. So it starts here, jumps to here, jumps here, jumps here, and jumps back to the starting point, and then just continues to go around and around. So let's say I had something like maybe I to the 13th power, and I wanted to simplify I to the 13th. So I'm going to try to use my highlighter so that you can follow me. In fact, maybe I'll get brave here and experiment with one of these other pointers. Maybe. Oh, okay. Let's try that. All right. So I to the 13th. What I'm going to do with that is I'm going to start at 0, and I'm going to just count around the circle. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And notice where you landed. So that I to the 13th, whoopsie daisy. All right, let's try that. Is just equal to I to the first. I gotta change. All right. And which we know is just I. Now the good news is if the number is fairly small, like 13 was, you can literally just go around that circle counting step by step. But if we had I to the 213th, we probably don't feel like sitting here and counting all the way to 213. So we do have shortcuts, okay? And what you're going to do is you're going to take the exponent, you're going to divide that exponent by 4, and whatever remainder you get tells you where you would, quote, land on the wheel. So going back to the example we just did, I'm going to go old school. If I took 13 and I divided it by 4 and I did my long division, I know that 4 goes into 13 at least 3 times, and 3 times 4 makes 12. And when you subtract them, you get a remainder of 1. So what it's telling you is you would have made 3 full revolutions or 3 full trips around it, and then you would have landed on I to the first, okay? If your remainder was a 2, it tells you land on I squared. If your remainder is a 3, it tells you you're landing on I cubed. Or maybe you don't have a remainder. In other words, your remainder is 0. That's just telling you you're going to land on I to the 0. So just keep telling yourself the remainder tells you where you land as you go around the wheel there. All right, let's try this next bear. So we're going to try to simplify I to the 23rd, right? So I'm going to go old school here, and you guys are probably laughing at me. All right, so old school long division. 4 goes into 23 5 times because 5 times 4 makes 20. And then when you subtract, you get 3. This is your remainder, which tells you you're going to land on I cubed. And when you look at your wheel, I cubed is -I. That's really as simple as it is. Now, if you had done that on your calculator, let's say you did 23 divided by 4 on your calculator, you would have got 5.75. So that 0.75, anytime you get a something 0.75, that's equivalent to a remainder of 3. If you used your calculator and you got like a 0.5, of course, that's a remainder of 2. If you use your calculator and you get 0.25, that's going to be a remainder of 1, right? And again, it just tells you where you're going to land on that wheel. Okay, so if you want to simplify this, believe it or not, multiplication is pretty nice. Do you remember the rule that says x to the m multiplied by x to the n is equivalent to x to the m plus n? Well, I'm going to take advantage of that rule, and I'm going to add the exponents. So when I add the 23 and the 54, we'll say I to the 23rd plus 54th. That makes I to the 77th. So again, we can grab our calculators, or I'm going to go old school. And 4 goes into 7 once. When I subtract, I get 3. Carry down the next number. Goes into 37 9 times. 9 times 4 is 36. Subtract them, I get a 1. So here's my remainder. So I know that I to the 77th is going to land on I to the 1st, which is just I. That's literally your answer. Now, believe it or not, this adding one's a little bit harder because these terms are not considered like terms. We cannot combine I to the 23rd with I to the 54th. I wish I could put a big stop sign up here on the screen right now. So what we're going to actually do is just simplify each of these terms individually as if they're in their own silo, kind of, so to speak. They're in their own little problem. So that I to the 23rd is I to the 3rd, which we saw earlier. So I'm not going to bore you by repeating all of that. But now what do we do with the 54? 4 goes into 54. Let's see. Once, subtract them, bring down the 4. So that's going to be 3, 12. Subtract them. Okay, I got a remainder of 2. So that's going to land on I squared, which is negative 1. Negative I minus 1 is my final answer. So here's what's going to happen. Of course, this is brand new. So this is going to be confusing for sure. But when we walk into class tomorrow, just start with this idea. Just divide your exponents by 4. Divide your exponents by 4. Focus on that remainder. If we can do that, I can help you with the rest and we'll be in good shape. And we can talk about interpreting these, what to do with that remainder and stuff. Okay, last but not least, we're going to get the FOIL. And we're going to go ahead and do a lot of distributing. And the big theme here is we're going to make sure we simplify our answers. We'll use pink for the last one. Let's take the 4 and distribute it to the 2. And we'll distribute it to the negative 5i. All right. Then we'll grab the 3i, distribute it to the 2. And we'll distribute it to the negative 5i to make negative 15i squared. Hey, that's a big catch right there. Did you see why I came up with I squared? Because I had to multiply this I by this I, which created that I squared. All right, a couple of things we're going to clean up. First thing we need to do is just to combine these two like terms in the middle. And negative 20 plus 6 makes negative 14i. And then the next thing I want to do is I want to replace this I squared with a negative 1. Every time you see I squared, replace it with negative 1. Replace it with negative 1. So when I multiply that negative 15 by a negative 1, I actually get positive 15. And then we're going to combine the 15 and the 8 to make 23. So 23 minus 14i is our final answer. So I hope you had fun seeing the introduction to these imaginary numbers. And I'll tell you what, with a little bit more practice, you're going to be scary good at these.